Why you shouldn't nest your code. Imagine a programming world where nesting code is a no-go. Shocking, right? Surprisingly, many, including Linus Torvalds, share this sentiment. Meet the never testers. They eschew excessive tabs and layers, opting for cleaner code. So what's a never tester? It's someone who doesn't excessively pile up blocks with functions. Discover their tricks to declutter your code. Are you ready to dive in? Never testers, a term introducing those who resist deeply nested code structures, are individuals who emphasize clean and organized programming practices. These developers avoid excessive code nesting, a practice that can lead to convoluted logic and decrease readability. The concept of never testers gains traction as it resonates with numerous programmers, including notable figures like Linus Torvalds, the creator of Linux. While not explicitly confirmed, Torvalds is cited in discussions regarding this coding philosophy. The approach champions code simplicity and maintainability, advocating for shallow nesting levels that enhance code comprehension. By avoiding intricate nesting, developers aim to create more straightforward, comprehensible code bases that are easier to debug, maintain, and scale. The notion of never nesters underscores the significance of balance between structure and clarity, promoting code that is accessible to both its authors and fellow collaborators. A never nester is a programmer who adheres to a coding style that resists excessive nesting of code blocks. This coding philosophy promotes keeping code shallow and uncomplicated, prioritizing legibility and maintainability. Nesting code involves creating multiple layers of an indentation within a function, which can lead to intricate, hard-to-follow logic. The impact of deeply nested code includes reduced readability, increased cognitive load, and challenges in debugging and modification. Never nesters advocate for structuring code in a way that minimizes unnecessary indentation, enabling a clearer flow of logic and easing the understanding of code paths. By emphasizing concise and straightforward coding practices, never nesters contribute to the creation of an efficient software, aiding in collaboration and long-term code management. This approach aligns with the goal of crafting code that can be easily grasped by both its original author and future developers. The depth of code nesting, visualized through the arrangement of braces, directly influences the complexity and readability of code. As code becomes increasingly nested, it can be likened to a series of Russian nesting dolls, where each layer encapsulates another. A function with only one level of nesting maintains a clear and concise structure, with limited indentation. For instance, a function with 3 levels of nesting presents a more intricate scenario. Each additional layer adds a new dimension to the code's logic, making it progressively harder to decipher. This is where the never nesters principle takes center stage, suggesting that code's maintainability and comprehension begin to suffer after 3 levels of nesting. Beyond this point, code becomes convoluted and challenging to manage. Even more daunting is the concept of 4-deep nesting, where complexity compounds further. This leads to code maze scenarios, where understanding the relationship between nested blocks becomes a labyrinth task. In the pursuit of coherent and manageable code, the practice of limiting nesting depth offers a pragmatic approach. By capping nesting at 3 levels, developers adhere to a rule of thumb that aids in producing code bases that are accessible, comprehensible, and conducive to efficient development and collaboration. Methods to nest code, namely extraction and inversion, offer strategies to simplify convoluted code structures and enhance readability. Extraction involves isolating segments of code into separate functions, reducing the nesting depth and clarifying the main function's logic. This process also enhances reusability and modularity, as extracted functions can be employed into various contexts. For instance, when dealing with a loop, extracting the loop's body into a separate function can significantly declutter the main function. This promotes a clearer understanding of the loop's purpose and its interaction with other parts of the codebase. Transitioning to the concept of inversion, it focuses on restructuring conditions to prioritize the main code path, thereby minimizing nesting. This approach entails flipping if-else conditions and rearranging the code to put the most common or expected cases first. By inverting conditions, developers can often eliminate the need for excessive nested blocks, enhancing the code's flow and accessibility. Both extraction and inversion techniques contribute to creating code that is more comprehensible, maintainable, and adaptable. By employing these methods, developers can transform intricate code structures into concise, well-organized functions that are easier to understand and modify, fostering efficient collaboration and software development processes. The inversion technique is a coding strategy that aims to reduce code nesting and enhance readability by reorganizing conditions within a function. This approach revolves around prioritizing the main code path while minimizing the need for multiple layers of nested blocks. Inversion involves flipping if-else conditions and altering the structure of the code to emphasize the primary execution path. For instance, by flipping an if-else condition, developers place the most common or expected case first, followed by less common or exceptional scenarios. This eliminates the necessity of nesting a series of blocks within the if-else construct. Inversion often leads to the removal of unnecessary else blocks. When the main path is taken, the else block can be omitted entirely, streamlining the code further. This simplification not only enhances code legibility, but also reduces the cognitive load on developers. The inversion technique can be applied repeatedly to create a chain of conditions that read like a checklist. This concise structure not only eliminates complex nesting, but also aids in understanding the various cases that the function handles. By employing the inversion technique, programmers craft code that is more comprehensible, less error-prone, and easier to modify, contributing to the overall efficiency of the development process. In applying the inversion technique to a more extensive code example, we encounter a scenario that involves managing downloads from the web. The primary goal of this code is to efficiently download files using an async process while handling various states of downloads. The download process involves a central class and interacts with a download thread. The thread manages multiple downloads concurrently, and each download is assigned a state: pending, in progress, or complete. The main loop orchestrates the download process by cycling through each download, deciding on actions based on its state. Within this context, the main loop plays a crucial role in driving download management. Applying the inversion technique to this example entails reordering conditions to prioritize the main execution path. By doing so, the code's readability improves, as the core functionality becomes prominent while complex nesting is minimized. This technique clarifies the logic of managing downloads, making the codebase more comprehensible and maintainable. The application of inversion here exemplifies the power of this strategy in handling complex real-world scenarios, streamlining code, and ensuring that developers can effectively grasp and manage intricate processes like downloading files from the web. Extracting and flattening code involves breaking down complex structures into simpler, modular components to enhance code readability and maintainability. In a download management example, the technique begins by extracting the pending and in-progress branches from the main loop. By isolating these sections, the code becomes more focused and their functionality can be understood independently. Moving the HTTP error section out of the main loop is another facet of this approach. By creating a separate function for handling errors, the main loop remains free from excessive nesting, resulting in a cleaner and more intuitive structure. Further extraction within the run function amplifies this process. Dividing the code into distinct sections like incoming request, current downloads, in-progress download clearance, and waiting for new downloads facilitates a step-by-step understanding of the download management process. The clear outlining of these steps in the main function delineates the entire download procedures, allowing developers to follow the logic seamlessly. By employing extraction and flattening techniques, the code base transforms from an intricate work of nested blocks into a series of concise, well-organized functions. This enhances not only the code's comprehensibility, but also its flexibility for future modifications and optimizations, making it an effective approach for tackling complex programming scenarios. Linus Torvalds, the visionary behind the Linux operating system, has notably advocated for an approach to coding that resonates with the principle of never testing. The philosophy is reflected in the Linux kernel-style guidelines, a set of coding standards employed in the Linux kernel development community. If you find this video helpful, then be sure to like, share, and subscribe to our channel. Meanwhile, thanks for watching.